So let's move on to the next speaker. The next speaker is Lorenzo Bellone, and the talk will be about in-the-air machine learning driven optimization of UAV coverage and resource utilization.
Good evening, everyone. I'm Lorenzo Bellone, and today I'm gonna present you my work, our work on machine learning-driven optimization of coverage and resource utilization in a UAV network. So this is the outline of this presentation, but let me just move directly forward to the background. We are dealing with UAV networks that basically whose main applications mainly depend on the role they can have in a wireless infrastructure. So they can be seen as mobile terminals of the network, thus exploiting all the services the network can provide, but they can also be used as network infrastructures, thus enhancing, let's say, the performance of the wireless network itself. Now, the architectures of UAV networks, of course, can be centralized, thus all the messages are routed through a ground-based station, and the UAV cannot directly talk to each other. But we can also consider the fact that we can also have a flying ad hoc wireless network. So UAV can communicate with each other, and usually this increases the coverage of the area we can consider, and also the flexibility of the system. Now, in other typology of communications that we can have in UAV networks regards cellular network and satellite networks, but let's say that for the moment, this is out of the scope of this presentation. So what we are considering actually is a FANET in which we have sufficient computing capabilities in order to process tasks that are forwarded from a set of ground users and that require a computational effort. And if you think about that, this is very useful when we don't have any availability of fixed infrastructures on the ground. So our goal is to propose a distributed framework that in real time can optimize metrics that can affect the quality of service of the ground users, such as the coverage of these ground users, the resource utilization of the network, but also the connectivity between UAVs, even if in our work we are not going to directly consider the connectivity between UAV. So what we want to exploit, let's say, is the mobility that the UAVs can have in order to optimize these metrics. So the fact that actually we want to exploit the dynamicity of this network. We consider, of course, we were inspired by recent works that consider similar scenarios, but let me just say that our contribution will regard the fact that UAVs are considered as computational entities in our case, and moreover, we are going to consider a distributed scenario. So we don't know all the information of our network, of our environment. What we know is just that UAVs will take partial observation of the environment and will perform an action accordingly. So we are going to formalize our problem as a partial observable Markov decision process, where each agent is a UAV that gets a partial observation of the environment and performs an action on the environment itself by getting also a reward that will depend on the level of coverage and resource utilization. Now, possible solutions for this kind of problems are usually tackled with reinforcement learning and swarm robotics. Let's say that for the moment, since we are considering not a very huge number of UAVs, we are working with a limited number, and also we are not properly considering a swarm, we are taking the problem under a reinforcement learning approach, but without discarding the possibility in the future also to work with swarm robotics algorithms. So we propose a multi-agent reinforcement learning approach, and more in details, a deep Q network approach, where each agent can take its decision since he has a policy that is learned through a neural network that is trained according to the experience the agent achieves during his interaction in the environment. So this neural network simply takes this partial observation of the agent and will output a value of each action, each possible action the agent can perform in the environment, and will select, let's say, the best action according to its partial observation. For simulation, for now, for the training of the policy, is a very basic simulation in Python where the agents can perform discrete movements in the two-dimensional space, and the ground users, we are considering a particularly dynamic scenario in which ground users appear according to a bivariate Gaussian distribution with rates that change over time. So each ground user will be also be characterized by a certain level of activity, which is basically a number that is proportional to the number of tasks that the ground user has to send to the network of UAV. So the coverage and the connectivity of UAVs are evaluated according simply to a given range, and the reward will be based on a normalized summation of the level of coverage our agent achieves plus the level of resource utilization of the UAV, which is basically the total amount of level of activities it observes from the ground users it is covering right now thanks to that action. So our approach, basically, our DQN implementation is based on two slightly different approaches. So in the first one, we consider an observation that is kind of centralized. Why I say centralized? Because all the agents will have the same observation, which is given by the positions of all the other agents in the network. So this is the input of our deep network, and the output, of course, will be our discretized action in the environment. So this is a very shallow neural network with just one hidden layer with 80 neurons, and here you can observe the parameters we chose for the architecture of this network. But let's say that the centralized observation, of course, is not so realistic, since we cannot suppose a priori that all the agents know the position of all the other agents without considering the possible connectivity we can have among UAVs. And so we consider we can rely on a more realistic observation each UAV can take by creating a relative map of the environment with partial observation regarding, for example, the level of coverage and the relative position of the covered UAVs, the covered device, then the level of activity that the covered device have, and then also the position of the neighbor UAVs. So we can we can create a convolutional neural network that basically will have as input these relative maps. And after the convolution step, we add also a linear vector, which includes also global position, global information of the UAV, just to let the agent orient himself in the environment. And here we have the parameters we select for this convolutional neural network. So let's say that the next step of our work is also to apply the policy we learn on Python to a more realistic scenario. So realistic scenario, let's say under the wireless communication point of view. And so for this scope, we use NS3, that is basically discrete event network simulator that allows for very realistic simulation. And also it could be integrated with ROS. So in our simulation, basically, we have the communication between UAVs that occur over an ad hoc infrastructure, while the communications between UAV and ground users occur with an infrastructure-based network. So basically, the ground users tend to associate to the drones, to the UAV, that in this case act as access points. So each node will have its own application. The UAV applications will regard the fact that the UAVs has tasks to process that come from the ground users, and also a sharing of information in order to allow the other UAVs, the other agents of our environment, to get a level of partial observation. So the ground users on their side will have to forward tasks to the associated access points, and then also to share information to the associated access point in order to share, for example, their position on their level of activity. All the parameters are shown here for the NS3 simulation. Now, how did we apply the policy from Python to NS3? We use a very simple toolkit that is named NS3 Gym that basically acts as a middleware between these two frameworks. So it basically it can handle all the exchange of messages between the NS3 simulation and a Python agent, and also manages the simulation timings. So thanks to this middleware, we can exploit an NS3 simulation as an environment in Python. So let me just show some results. In this first scenario, basically we exploited 2 drones and 3 clusters of ground users, where the size of each cluster changes over time, while the level of activity of each ground user is kept on average constant. So here we can see how the 2 approaches, so the one based on the centralized observations and the one based on the more partial, so the convolutional neural network, more partial observations, reach the same level of rewards. And also we can appreciate how actually the drones move towards the most, let's say, populated clusters, even when the size of the cluster right now changes, and so the UAV tends to change also the cluster, moving towards a more populated one. In the second scenario, basically, we still have 2 drones and 3 clusters, but this time we have a size of each cluster that is the same, and the level of activity now is changing. Let's say that the reward in this case is not changed. So we basically want to see if the agents learn how to behave in different conditions according to slightly variation in the environment, where they have to understand whether to optimize the coverage, but also to optimize the utilization of the network. So to cover the most active users in order to process the tasks that users send to the network. So in this case, we can see that the convolution of the partial observation has a higher variance in the reward, but actually we can also appreciate how the agents move towards the most active clusters that in this case are represented by the green clusters, even when they change. So let's say that after the policies have been trained on Python, we want to apply them on the NS3 simulation. So the results right now that I'm going to present are related only to the centralized observation, to the centralized policy, because let's say that for the partial observation, we are still working on making the observations we get on NS3 more coherent with the one we get in Python. So for now, let's say that we have poor results for the partial observations one. So using the centralized policy, we can appreciate how both the drones tend to reach 50% of coverage each. So the summation is very close to 100%, apart from these peaks that, of course, are correspond with the moment in which the UAV tends to change cluster and move towards a most populated or a most active one. The level of task completion ratio, let's say that right now it's not very meaningful, but it should give an idea of the resource utilization of our UAV network, and it becomes meaningful when we compare it with other approaches. Now, in the videos of the NS3 simulation here, we can see actually agents that change clusters according to the size and activity, even if, and I'm sorry about that, with the NS3 visualizer, we cannot change the colors of the nodes, and we cannot show how the nodes change in the cluster change in their size. So for the comparison of our approach, we started with very simple baselines, so baselines approaches, so random actions and fixed positions. In the fixed position, basically we just select 2 clusters out of 3, and we position there the UAVs without letting them move during the episode. And we can see how actually our approach performs better in terms of coverage and task completion ratio, since let's say it adapts better to the variations of the environment with respect to the variation of the size and the variation of a level of activity. So let me just conclude this presentation. Basically, we propose this framework, this distributed framework, in which each agent tries to optimize the coverage and the resource utilization, where in a UAV network that basically has computational capabilities in order to process tasks that come from a set of ground users. Now, our approach is based on a multi-agent deep reinforcement learning, a DeepQ network, more in details, and we exploited 2 different observations, 2 slightly different observations that each agent can take. So a more centralized one and a more partial one. In the results, we can appreciate how in both approaches, the agents tends to optimize their metrics of coverage and resource utilization, even if we should better work on the convolutional neural network. So we have to better tune the hyperparameters, or let's say create a better architecture in order to make it more robust to some variations we can have in the environment. And so apart from this, other future works will be to study also the scalability of the system, for sure, because we are not going to work with just the 2 UAVs, but we hope to work with more than with more UAVs. So we have to study the scalability and the flexibility. And then we have also to improve the policy transfer. So applying the policy from Python to NS3, but not only applying the policy, but maybe keep on training this policy in another simulating scenario. So keep on training the policy on NS3. So when we have a more robust scenario, a more robust approach, we can also compare this approach with more sophisticated algorithms, such as some swarm robotics algorithms or also other methods. And then we can eventually and possibly, we can also try to apply our algorithm in a real world scenario. So this is the end of my presentation. Thank you very much for your attention. And if you have any question or suggestion, I will be very glad to take it.
Thank you very much, Lorenzo. As usual, let's wait for a few seconds for the Q&A. Could you elaborate on how you tune the hyperparameters? Do you follow any principled method?
Yeah, well, let's say that we base our approach on basic DQN. So we read the original papers of DQN, and I also apply, let's say, from literature review, I also apply similar architectures. But as usual, the hyperparameters follow also a very high, how to say, trial and error procedure. So yeah, that's how we did it, and we should keep doing this, because we need, of course, a higher tuning of parameters and a better tuning of parameters, but as always, let's say.
So, Lorenzo, thank you. I mean, a virtual round of applause again.